Okay. See here. Now whatever we are transmitting the signal, that signal strength, whatever we are transmitting, that signal strength will not be same at the input of the receiver. Is it right or not? Why? Because the signal strength, whatever we are transmitted, now is a transmitting antenna and it is passing through a various channel losses. Okay. Now absorption losses, attenuation losses, distortion, scattering, right? So many losses. Therefore, due to those losses, the signal strength received from the antenna in any communication system is not constant. Now, which is also called as, this effect is called as fading. This fading occurs due to various propagation losses. Now, if suppose if you maintain the overall gain of the receiver is constant, means input is coming, receiver gain is constant, not like this, constant, fixed one, then what happens? Definitely the output is changes, output signal strength is changes. No, what we want? So we replace this, instead of finding a constant gain, I just find a overall gain. Okay, variable gain. So AGC circuits, the role of AGC circuits, automatic gain control circuits, will vary the overall gain of the receiver. The AGC circuits will vary the overall gain of the receiver according to the variations of the signal strength. Whatever may be a signal strength is coming, now according to that particular signal strength, the overall gain of the receiver is varied according to the signal strength, such that it will maintain a standard output. Okay. So whatever the signal strength is coming at the input of the receiver, then the overall gain of the receiver is varied to maintain a standard output. Okay. Suppose if AGC circuit is to maintain a constant audio output irrespective of the variations of the input signal. It may be a 0.1 or 0.1, 0.2, 0.3, 10, whatever it may be. The gain is changing. It may be sometimes increasing or decreasing according to the variations of the signal strength and to maintain the standard output. Therefore, whatever the super heterodyne receiver which we are studied, now in that particular circuits, then this AGC circuit is also used for the purpose of vary the overall gain in order to get the standard output irrespective of the variations of the input signal. Okay, hold on. Clear or not? Okay. Now we'll see the FM receivers. Now, before we see the FM receiver, I just want to study the two circuits, free emphasis and de-emphasis. Now, why you use this free emphasis and de-emphasis circuits in FM? Why it is not used in AM? Okay, that also you can have a question in your mind. So we'll clarify that one also. First of all, what is the free emphasis, de-emphasis? Why the free emphasis? What is the use of free emphasis? Why it is coming? Now that we also will see. Now see here. Now this is audio signal strength, a power of the audio signal. versus frequency, means power distribution of the audio signal versus frequency. This is called as power spectral density. Power of the audio signal over a frequency range is a power spectral density now of an audio signal. This is power spectral density of an audio signal, power over a frequency range. Therefore, power spectral density units are watts per hertz. Okay. Now, similarly, this is the power spectral density of a noise signal. This is the power spectral density of a noise signal. Why? Because you know that the noise power is directly proportional to bandwidth. As bandwidth is increases, noise power is increasing. That's why I am writing like this. As frequency is increasing, therefore this noise power is increases. As frequency is increases, this noise power is also increases. Okay. So this is the power spectral density of an audio signal, and this is the power spectral density of a noise signal. Okay. So now if you see here, this is the audio. Audio means 20 Hz to 20 kHz range. In 20 Hz to 20 kHz range, now I just divide into three parts. Now this is low frequency range. And this is mid frequency range. Now this is high frequency range. Here, this is the low frequency range, this is mid frequency range, this is high frequency range. See, don't confuse high frequency, mid frequency. I am talking about audio signal. Audio signal frequency range is just 20 Hz to 20 kHz. Within this 20 Hz to 20 kHz ranges, I am categorized low, mid, high. Okay. Now come to here. What happened now? Now at this particular low frequency, now the signal strength, and what about the noise? Noise is very, very less. Signal to noise ratio, which is good, high. What about here? Signal and noise almost same. Signal and noise both are same approximately. But what about here? Now signal strength, but the noise power is more. Noise power is very high. Therefore, the signal to noise ratio, which is very less. Signal to noise ratio, which is very, very less. So now what happens? When the signal strength is less, signal to noise ratio is less. This information is okay. This is good. This information is okay. This information is okay. But this information is lost, because noise is dominating at this particular audio component. Am I not? Now this particular information is lost because here the effect of noise is more. Noise is dominating. Effect of noise is more at this particular stage. Noise is dominating. Information is lost. So what should we do is, now in order to save this information, so I want to save this information. Save the high frequency audio information pre-emphasis circuits are used. What is the pre-emphasis circuit? What is the pre-emphasis circuit? Now see here, to save this highest audio frequency component, pre-emphasis circuit is used. What is the pre-emphasis? Pre-emphasis circuit. The pre-emphasis circuits are used to boost the high frequency audio signal strength. Pre-emphasis is defined as a process of boosting. This signal strength should be boosted. This signal strength is boosting. The pre-emphasis is defined as a process of boosting the high frequency audio signal strength in order to negligible the effect of noise. When this signal strength should be very high, so signal to noise ratio should be definitely, the signal strength is high, the noise domination is less, signal to noise ratio is high, and which should be eliminate the noise and signal without losing, then it will be appear at the output of the receiver. Okay, so this pre-emphasis, note down, the pre-emphasis is defined as the process of boosting the high frequency audio signal strength such that maintain signal to noise ratio is greater than 1. Such that maintain the signal to noise ratio is greater than 1, information is saved. Information is not lost. Information is not lost. Clear? Boost the high frequency audio signal strength such that maintain the signal to noise ratio is far greater than 1 and information is not lost. So this is the pre-emphasis. See here, this is the pre-emphasis circuit now which is used. This pre-emphasis is used at the transmitter before modulation. Okay, now this pre-emphasis process is used at the transmitter. This pre-emphasis is used at the transmitter before modulation. This pre-emphasis is used at the transmitter before modulation. Okay, now the students are asking what you are doing with the pre-emphasis technique. Now what is the meaning of pre-emphasis? This audio frequency is reproduced at the output of the receiver. This audio frequency is reproduced, but this audio frequency is not able to reproduce without pre-emphasis. So now pre-emphasis is a process. Successfully this audio frequency is reproduced at the output of the receiver is called as fidelity. Now what is the another one? The pre-emphasis will be done to improve. The pre-emphasis will be done to improve the fidelity of an audio signal. The pre-emphasis will be done to improve the fidelity of an audio signal. Okay, so the process of pre-emphasis is nothing but improving the fidelity of an audio signal, right? This is the process of pre-emphasis. This will be done at the transmitter before modulation. Exactly the reverse operation is nothing but the de-emphasis. Okay, because this is not the original information. This original information is boosting. How much you are boosting, you should be again get back at the receiver side. So the exact reverse process is nothing but de-emphasis. De-emphasis is used at the receiver after demodulation. Okay, after demodulation. Now we'll see the frequency characteristics of pre-emphasis and de-emphasis. Now we'll see the frequency response characteristics of pre-emphasis and de-emphasis circuits. Before that, you note down this. Okay, now we'll see the frequency characteristics. Now see here. Now this is the frequency response of preemphasis and deemphasis circuits. Now see here. Now at this particular frequency, let us assume this is some F2, this is F1. Up to this particular frequency, signal to noise ratio is good, therefore there is no need to improve the signal strength. It will maintain the same signal strength, means gain is multiplied with 1. But where the effect of noise is more, therefore there we will boost the signal. Now see here, now here the effect of noise is more at high frequency in the audio signal. Now there the signal strength will be increased. Okay. Now this is nothing but a free emphasis characteristic. Ever know? This is free emphasis. Now exactly the reverse process will be done at the receiver side after demodulation. Now that is nothing but the de-emphasis, because now it is transmitting, noise is affected, not a problem, signal strength is more, noise is affected but the signal strength is more, this signal strength will not last. So now at the receiver side, now after demodulation I want my original information, but your original information strength is increased, so you can get back your original information. So now up to this particular frequency, not a problem. Now see here. Now this is F1, this is F2. Now at this particular frequency, now this gain is decreased by a factor of 1000. Now this is de-emphasis circuit. Exactly the reverse operation of free emphasis is nothing but here. Where you are boosting, now at the same thing will be getting original signal attenuated by an amount of how much you are boosted. Okay. Now this is the de-emphasis. De-emphasis circuits are used at the receiver after demodulation. What is de-emphasis? Exactly the reverse operation of free emphasis is nothing but de-emphasis, right? Now the free emphasis is used to at the transmitter before modulation. Pre-emphasis is a boosting of the high frequency audio signal strength such that the signal noise ratio is greater than 1 for all frequencies. Now similarly, the de-emphasis is exactly the reverse operation of pre-emphasis. So this is used at the receiver and after demodulation. Okay. Now a simple RC circuit will act as a demodulator, de-emphasis, because this is a negative slope, which is falling slope you can pole. Therefore, this is the de-emphasis circuit. And pre-emphasis is nothing but amplifier is required, right? Our lead compensator is nothing but a pre-emphasis circuit is used as a, the lead compensator is also used as pre-emphasis. This is amplifier. So this is the pre-emphasis circuit. An amplifier is used as a pre-emphasis. A simple RC circuit is used as a de-emphasis. Okay, note down this. Now, I'll just write a few points. In AM, the audio signal is band limited to, in AM, the audio signal is band limited to 5 kHz. So, signal to noise ratio, which is greater than 1 up to 5 kHz. Is it right or not? In AM, the audio signal is band limited to 5 kHz. So, signal to noise ratio is greater than 1 up to 5 kHz. Therefore, preemphasis and de-emphasis are not used in AM radio. Okay. So in FM, almost all the audio signal is band limited to 15 kHz. Band limited to 15 kHz. Therefore, the preemphasis and de-emphasis circuits are used. Preemphasis and de-emphasis circuits are used in FM radio. To improve the quality of audio signal, in music systems, DVDs, CDs, the free emphasis will be done up to 20 kHz. The free emphasis will done up to 20 kHz. The preemphasis and de-emphasis circuits are used to reproduce a high quality of audio signal in a music systems called as, this method is called as, if you use for getting a high quality of audio signal in a music system, if I use the preemphasis and de-emphasis circuits in that particular music system, now that music system is called as Dolby noise reduction system. Dolby noise reduction system. You may observe this point. you can also observe this point. So if you go to the multiplex or theaters, so now before the movie starts, now you add one, you see one ad. This theater is having a features of Dolby music system. Now what is the music of a Dolby music system? A Dolby music system means for getting a good quality of an audio signal at the transmitting side, they are using preemphasis circuits in the audio signal transmission. At the receiver side, they are using a deemphasis circuit. Okay, that is called as a Dolby music system, means a Dolby noise reduction system. The Dolby is not a scientist name, it is a lab name in US. Okay, United States of America, one lab is name is Dolby. Now actually in that particular lab, they are they are introducing this preemphasis and deemphasis circuits in a music system to get the best quality of the music. So that's why this is called as a Dolby noise reduction system. Okay, so this is a Dolby noise reduction system, and this is the preemphasis and deemphasis circuits used. Okay, now that's why see here the bandwidth of FM, which is equal to 2 delta F plus 2 FM plus God band. This is actual bandwidth of FM signal, because you know that FM requires more bandwidth. Now see here, this is 2, practical frequency deviation is 75 kHz. 2, the highest frequency in FM is band limited to 15 kHz. How much? 150 plus 30, 2 into 75, 150 plus 30, 180 plus 20 kHz is a God band. So without overlapping and for successful recovery of the signal, the God bands are maintained between the modulated signal, and band pass filter practical designing is also easy because it is not having a sharp cutoff frequencies. So transition bands are entering into this God band. So this is actually the bandwidth of FM, and that's what you are saying, the bandwidth of FM. How much you are writing? 200 kHz is the bandwidth of FM. 150 plus 30 plus 20, 200 kHz. Okay, now this is the preemphasis and deemphasis circuits. Now we will see the exact FM receiver. Okay, now you first note on this. And this preemphasis circuit is nothing but a lead compensator. This is a lead compensator circuit. Now this is FM super heterodyne receiver. Now see here one by one. Now this is the RF amplifier. Now here the carrier frequencies are 88 MHz to 108 MHz. Now this is RF amplifier. Now here the carrier frequency is 88 MHz to 108 MHz. Now this is the RF amplifier. Now this is mixer, you know that a mixer along with the tuned circuit is called as pre-selector, right? An RF amplifier is also used a tuned circuit in order to improve the image rejection ratio for further. So this is also a tuned circuit. You know the characteristics of the tuned circuit and all these things, how it should be. So the mixer job is to down convert any incoming signal to IF. What is IF here? In FM, FL minus FS, which is equal to IF, which is equal to 10.7 megahertz. Now this is IF amplifier. Now this IF amplifier is also having a tuned circuit, and this tuned circuit will act as a band pass filter. Now this tuned circuit acts as a BPF, band pass filter. Now this is the gain versus frequency characteristics of the tuned circuit. How the gain versus frequency characteristics of this tuned circuit. Now this is the gain versus frequency characteristics of the tuned circuit. Now this is IF fixed, which is 10.7 megahertz. And this is the bandwidth, which is nothing but 2 into beta plus 1 into FM, which is equal to 200 kilohertz. Now I am asking one question. Why this IF is increased? In AM, IF is only 455 kilohertz, but in FM, the IF is 10.7 megahertz. Why it should not decrease? Why it is increased? When IF is increases, you know one advantage. When IF is increased, the separation between FS and FSI is increased. This gap is increases. When this gap is increases, gain at FSI is decreases such that the image rejection ratio is increased. There are two techniques to improve the image rejection ratio. One is quality factor is increases, which is not at all preferable. Another one is intermediate frequency increases, which means rho is increases. That's why in IF intermediate frequency they are fixed at 10.7 megahertz. Okay. Now this is IF amplifier. Then after IF amplifier there is a demodulator, but here there is a extra circuit which is used in FM receiver. This is amplitude limiter. Okay, what is the use of amplitude limiter? I will tell you. This is the amplitude limiter. Now this is the amplitude limiter, an extra circuit here which is not there in AM, which is there in FM. So this amplitude limiter is nothing but this is IF. Now go for demodulation. Demodulator convert IF to demodulator converting IF to AF, IF to AF. Now this is AF amplifier. And this is power amplifier. Now that is AF amplifier and this is power amplifier. And this is loudspeaker. Okay. So after that here also there is a small change. After demodulation, this is FM receiver. After demodulation, because we are using for good quality pre-emphasis at the transmitter side, therefore we have to use de-emphasis circuit. De-emphasis which we want to use here at the receiver. Okay, so now This after de-emphasis, demodulation, de-emphasis circuits are used. Then this is original AF. Okay, this is boosting AF. This is original AF. Now this is AF amplifier. Increase the audio signal strength for further. And this is power amplifier, impedance matching, and these together to improve the quality of the audio signal strength. Then you can get the standard and a good quality of voice signal, audio signal, loudspeaker. Okay. Now this is the actual super heterodyne receiver of FM super heterodyne receiver. Okay. So here you know both are connected in cascade. Overall gain increases, image rejection ratio increases, and image frequency is completely suppressed. This tuned circuit is especially for image suppression. If this tuned circuit is used, further it is improve the image rejection ratio. This circuit acts as a band pass filter for allowing the intermediate frequency. Okay. Now what is amplitude limiter? Now FM demodulator means, FM demodulator is what? FM demodulator is frequencies to voltage converter. Voltage converter. Am I not? FM demodulator is frequency to voltage converter. The problem is due to noise, FM signal envelope is not constant. We know that any modulated signal envelope is not at all the same one what we are transmitted because of the noise. FM signal envelope is not constant due to noise. Amplitude distortion will occur. FM signal envelope is not constant due to noise. Amplitude distortion will occur. Am I not? Amplitude distortion will occur. So due to noise, whatever the FM signal means, envelope should be constant. But due to noise, then the noise is coming and affect the strength. So envelope is not maintained constant. If envelope is not maintained constant, now that is nothing but the amplitude distortion. Okay. Now if envelope is not maintained constant, if envelope is not maintained constant, not possible to convert frequencies to voltages. Demodulation not successfully done if envelope is not maintained constant. Therefore amplitude limiter is used. Amplitude limiter is used to eliminate the noise, and to maintain constant envelope of FM signal. And to maintain constant envelope of the FM signal, when FM signal envelope is maintained constant, and it is possible to convert frequency variations to voltage variations. The demodulation is successfully done. Okay. Now, amplitude limiter is not used in AM because in AM the information itself because the information itself in the form of amplitude, the information itself in the form of amplitude. Okay, now that is the reason why the amplitude limiter is not used in AM super heterodyne receiver. The amplitude limiter is used in FM super heterodyne receiver because due to noise, whatever the FM signal is transmitted not same as the input to the receiver, and that envelope, because in AM amplitude of the carrier before modulation, after modulation is changed because that is amplitude modulation, but in FM frequency amplitude of the carrier before modulation is constant, which is AC. Amplitude of the carrier after FM modulation is also constant, which is AC, but that envelope is disturbed due to noise. The amplitude distortion will occur. Now that distortion is avoided by using amplitude limiter and to maintain a constant envelope such that the possible to frequency conversions to voltage variations. Frequency variations are converted to voltage variations such that you can get back the original information signal, audio signal. Okay, now this is the FM super heterodyne receiver. Okay, clear or not? This is the FM super heterodyne receiver. So therefore, this is the FM receiver is the best one, and no noise, nothing. Therefore, now for audio signal transmission, FM is best. Therefore, AM versus FM finally we'll see. AM versus FM. Now one by one I am explaining. See here first. First one is with respect to power. With respect to power, how? Both. The total power, which is equal to PC into 1 plus mu square by 2. Now the total power, which is equal to PC, which is equal to AC square by 2R. Am I right? Not. So AM requires more power. FM requires less power. So the power efficiency out of total power, how much power is carried by side bands, which is nothing but mu square plus 2 plus mu square, and maximum efficiency is 33.33%, which is very less. And here the power efficiency, which is out of total power, how much power is carried by side bands, Now this efficiency, which is 100% for beta equal to 2.4, 5.5, 8.6, 11.8. Okay. Now this is with respect to power. Now second comparison with respect to bandwidth. Now bandwidth, which is equal to 2 FM 2 omega, AM requires less bandwidth. Now bandwidth here, which is equal to 2 into beta plus 1 into FM. FM requires more bandwidth. Right? Now independent of modulation index. Bandwidth is independent, but here bandwidth is depends upon modulation index. One more point also I missed here. Now here power is depends upon modulation index. Power depends upon modulation index. Now here power is independent of modulation index.